Hello, everyone. Let's get started with this session. I'm Aritra Ghosh, and with Adam Bolton, I will be chairing this session. Just a few reminders about the code of conduct. The full code of conduct list is at this QR code. And if you experience any violations, please reach out to the contacts listed. For folks who are on Zoom, please keep yourself muted. We'll be monitoring both the Zoom chat and Slack for questions. And a note about COVID, which I was asked to remind all of you about. I think there have been 2 participants who have come down with COVID, and they have been asked to reach out to folks who they have had contact with in the past few days. So look out for those messages. Now, with that said, let's get started with this session. So this session was primarily born out of this initial discussion that we had at the Informatics and Statistics Science Collaboration meeting a few months back that Adam and I were talking about. And the basic idea is that for various Rubin science cases involves processing or reprocessing some part of imaging data. And hopefully through this session, we'll have some idea about how, as potential users of Rubin, you can go about doing that. So what we'll do is we'll begin with a talk by Shenming about kind of as an example of what kinds of science is possible with such large-scale processing. This will be DECam processing of data using LSST pipelines. Then we'll move to a talk by Adam Bolton, who will be talking about the USDF. And finally, we'll have a talk by Christina Williams, who will be talking to us about the cutout-making service that is currently hosted on the RSP, and then where it might go in the future. We envision this being a very interactive discussions. The speakers might not have the answers to all your questions, but our hope is that through this discussion, we'll move forward. So first, I would like to invite Shenming to come up here and give the first talk.
So hello, everyone. Sorry. Good afternoon, and thank you for coming. My name is Shenming Fu. I'm a postdoc in NORLab. Today, I want to talk to you about this DECam multi-manager astrophysics pipeline. So I did this work with my team members, Tom, Aaron, Yuan, Sebastian, and Destry. So I would like to thank the organizers for giving me this opportunity to show what's going on. Yeah, so I think in the talk I would say MMA many times. So MMA means multi-manager astrophysics or astronomy. So I will first give you some background, then give you some examples of DECam image suppression using the Rubin pipeline. Then we'll tell you a little about the real bogus calculation using PCA, and finally give a summary and the future work. So I would like to make some connection with the topic of the session. So maybe we can start to with this, like some Rubin science cases. And we know for different science cases, we need different processing methods. So I was just thinking maybe we can divide, the topics into 2 sections. One is specific targets we are interested in, maybe some single, special, small sky region on the sky. So for time domain, that's very common. So we are looking at some variable stars, supernovae, some transients, or even like AGN, or some specific special stars or galaxies. And for those targets, we only interested in the information inside a small area. So we need cutouts. We don't need the information outside. Another case is statistical patterns. So we need to look at many objects. We want to look at a large sky region. So for example, we are looking something pretty local. They're very close to us. They look very big on the sky, or Milky Way. We want to look at the interstellar median or the motion, the pattern in the motion of like objects. So another case is weak lensing or large scale structure, because if we only look at one galaxy, we don't know anything. We need to look at many, many galaxies and find pattern from their shapes or the distribution of those galaxies. So another case I want to mention in the middle is nearby galaxies or like giant ellipticals, because they're so close to us. When we process their data, we need some special ways to, especially the background subtraction. You might heard something in the LSB session in the morning. Especially for the weak lensing, we are interested in the shape of individual small galaxies. But for the nearby galaxies, we need a different way to deal with the background subtraction. So for background suppression, for source detection, different science cases need different processing methods. So that's why reprocessing is very important, because I believe different researchers have their different ways to do this. So there are also many other cases. I'm just giving some. Yeah, so now I want to talk a little bit about Rubin pipeline and the DECam data. So just make a quick comparison between DECam and ST. The field of view, DECam has 3 square degree, then Rubin's about 10. The depths, if we just think about R band, 30 seconds and 5 sigma point source, then the depth is around 23.5 versus 24.5. And the pixel scale is pretty close, 0.263 and 0.2 per second. And for the band, both they have UGI-ZY, and DECam also has VR, the very wide band, also narrow bands. And the good thing is that the IST pipeline can process DECam data. I was pretty lucky during my grad school time and my first postdoc. I have a chance to use the Rubin pipeline to process DECam data, but for very different science. For the static science, I have a chance to process the galaxy cluster data for this local survey. You can find more details in Anthony's talk yesterday. And then for my postdoc, I work on time domain, so to build a pipeline for MMA. The good thing, if we think about DECam and IST pipeline, is we can use DECam data to test the software. So we can find those results to predict how the Rubin would perform. But backward, IST pipeline can provide us very nice algorithms. So, and also the data format will be compatible to Rubin. So it's very easy to make comparison. Yeah, so the next thing is MMA. The goal here is just to look for the EM counterparts of gravitational wave sources. And this is just a tool we wanted to serve as a tool for the entire astronomy community from NORLab. So why we want to use DECam to do this work. First, DECam observed this kilonovae, right? Everyone knows that. And then DECam had a very large field of view, had very good depths. And the Rubin was spent up to 3% time for TOO, and the cadence 3 days, but not the same band. And later years, there could be a rolling observation. So DECam can fill the gaps in the SST observations. And also, if we just process the data, the IST pipeline are processing the data pretty quickly, just a few minutes. And also you can run things in parallel. If you use better hardware, maybe it's faster. So the scale is similar to the exposure time and the overlaps. So that's good. But there are some other problems we need to think about. The MMA observation is very special. If we just want to observe kilonovae, we cannot get many exposures because kilonovae change the brightness very fast. And if you want to search that, the sky area is very, very big. It's like tens to hundreds of field of view of DECam. And because we don't have many exposure, we might be affected by the weather conditions. And if we just look at history, we might not have a lot of archival observation for training. So we think maybe we can just do real bogus calculation at single exposures rather than we get a lot of exposures and look at many exposures. We just do this in single individual exposures. And also we want to use unsupervised learning because it's straightforward. It won't be limited by the training set. And the other thing is we don't have many archival data for templates. It's possible this kilonovae just show up at somewhere without any previous data. So here we just want to test different ways to make templates. Okay, so in summary, we need a DECam pipeline to quickly produce the candidates per exposure. So let's just see how it looks like if we run image extraction on those DECam data, how the pipeline can give us. So we just use the AP pipeline, the alert production pipeline in the Rubin pipeline, and we use this. The older version is version 19, it's Gen 2, but later we also test Gen 3. There's no big change here, and we use archival data. So there's no old data; those all in the history. For this kilonovae, I want to show you the light curve. So those blue points, those are the data. On the left is PS flux. Those are the flux measured from the difference image. And total flux measured from direct image, the science image. And also want to tell you, this is from the force photometry. So basically the AP pipeline can associate the DIA sources, the sources in those difference images, and then run force photometry on that. So the light curves come from force photometry. One thing very interesting we find is we can connect the light curves with the weather condition, the observing conditions. So the DECam doesn't know anything about the weather. But if we compare the weather with the light curve, we can understand the light curve better. So for example, the red point, the red triangles here is pointing out where the low T effective, like low exposure, effective exposure time exposures are. So T effective is some term from CTIO from the for available for observers. If it's very low, that means the exposure is not very good. And then on the right, those large scene, I use a purple color, those purple triangles to show where the scene is pretty big. So you can see if it's low effective, you can get a large error bar. And if it's large scene, you can get a large fluctuation in the light curve. So it's very nice to see the consistency between the weather condition and the light curve. Also, we think the difference image flux is less sensitive to the weather and can give you clear light curves. I think that's. And on the right is just one exposure. I don't know if you could see a gray take here. It's basically where that exposure is. I'm showing you the difference image and the direct image and the template. Yeah, so there's some other examples. If you think about like supernovae. So the first one is a type 2 supernovae. On the bottom is type 1a. Probably it's from DS. We select a very bright supernovae. But again, you can see where this the weather conditions not very good, and check that whether it can tell you something in the light curve. And then on the bottom is from the DCAT DDF. Yeah, especially this one from the total flux from the direct image. So you cannot see very clear pattern, but from the difference image light curve, yeah, it's very clean. Just mainly because this supernovae is pretty close to the galaxy center, so blending is pretty strong, but use the difference image, you can definitely get better results. Okay, so this one is a supernovae candidate, also from DCAT. You can see this fluctuation around MJD 59325. So you can see a similar pattern here, but at a different star. So those are caused by weather. But using, if we plot weather conditions with the light projector, we can clearly see what's going on. At the bottom is another example. We are thinking about stellar flares from this DWF survey. So we just reprocess the data. And this light curve is very similar to the light curve in that paper, but using very different pipeline. But again, you can see very different data, and we process that with the Rubin pipeline, and we can get light curves and the images. Those two last examples, we switch into variable stars. On top, crater 2 is a diffuse dwarf galaxy. So the goal of that paper is looking at our stars, variable stars. and we just check the light curves, and you can see one with big error bar and big fluctuation. You can understand it easily from the weather. And the bottom is the galactic bulge. So we are using those 5-second exposures from Set et al. So we are looking at an EPC variable. So at the bottom, those are the light curves from difference image and direct image. And because we can know the period from OGO, so we can shift the light curves. So from the difference image, you could see something like those. Those are, I think, very likely caused by saturation. But for the star we're interested in, it's actually pretty good. So that would connect to something I want to talk about later. For saturations or like artifacts, how do we deal with that? I learned a lot from this paper, Liu et al. So what they did was they're using image simulation, basically DC2, desk DC2, and they use source injection. Then they know what they ingested, they know what is real, and they can check how those things look like. After processing their simulated images with Rubin pipeline, they will know how the flags are performing. So earlier I mentioned that we could do real box collocation at single exposures. So here we are looking at the catalogs of individual difference images. The first thing you want to do is to clean the catalog with those flags. And then basically we are looking at two types of flags. One is related to flux, one is related to the geometry. We check those flags with the real objects, mainly the kilonovae, other things I showed before. And we think those flags are pretty useful to remove artifacts. So after we remove some artifacts using the flags, we want to do some classification. So here is not really fun to find a kilonovae. We just want to find candidates. We just want to find something very likely real and make sure we can remove artifacts as much as possible. So before we run PCA, we need to standardize the features. And for the PCA, we consider 3 types of features, like signal noise, like the ratio of flux, and the geometry. Signal noise is just the flux measured on the difference image, and the ratio is the flux on the difference image versus the total flux on the direct image. And for the geometry, basically, those are the size of the object, the shape of the object, and some related terms. Again, we check those because we know the catalog of individual exposures. We can check real objects like kilonovae, how those features look like. So we select those. You might see some negative sign here. Why we want to use negative? It's just after running PCA, we want the feature of those individual features of a real object has larger or greater value than other things. So for example, if something is very round, definitely the epicity will be close to 0. But if something has large epicity, this term will be big. So use a minus sign can make sure a round can have greater value than others. So for example, for the PCA, if you run that for the kilonovae data, after, well, just for one CCD chip, and then we know where the kilonovae is. After we filter our things using the flags, only 4 sources remain. Then we can run PCA, and you would get the values of PCA1, PCA2, those 2 values on the space, PCA space. And basically we want to look at the PCA1 value. If it has a PCA1 value, it can tell us it's good. So for this target kilometer here, it does have a very large PCA1. Something on the right I want to show is the T effective telling you the weather. If the weather is not good here, the T effective is not very high. But maybe just because this kilonovae is very bright and the image is clean, so the EVR is the explained variance ratio. If it's big, that means the separation is big. If it's the separation too big, that means the separation is good. So in this case, the performance is pretty. And the last image is QP is just a quantile value. If we think about for the PC1 value of those 4 points, what's the quantile of individual points? That's like a metric, like how the target we are interested in stand out compared to others. So we can just do the same thing for many, but for this kilonovae data, in G-band, unfortunately, only the first 4 exposures, the kilonovae is very bright. For the later ones, it's actually below 5 sigma. Previously, you can see very nice light curve, just because it's running post-photometry. So even when the kilonovae is below 5 sigma in single exposures, post-photometry can still stand out. But if we just use individual exposure, we don't know where the kilonovae is, and we set the detection level at 5 sigma, then after first 4 exposures, we cannot find. But here, I just want to show you, if we run the PCA and look at those different Q, those different features, how the quantile or the rank. At the beginning, it had a very high value, but later it becomes fainter, so the value becomes small. But here, the QP is the PCA1 quantile. It's almost 1 at the beginning, and later it becomes lower. So that just tells us when the kilonovae is bright enough, the performance is good. So another example is the supernovae, one of supernovae I showed you before. We did the same thing. You can see for the top, on the top, that exposure, the T effective is very low, close to 0, because the weather conditions not very good. But even when the weather conditions not very good, the EVR is not very small. So in that case, the target, the supernovae still has very large PCA1 value compared to others. And the other exposure is like a couple of exposure later. The T effective is large down, so the weather is good now. Then the EVR is even larger. So that means the performance is even better. We can do the same thing and just consider many different exposures. As many exposure, we can detect this supernovae as possible. This image is just showing you where that supernovae is. So because the supernovae is getting fainter and fainter, we can use that test, like when something's starting from the large signal noise to lower signal noise, how the performance would look like. So we just look at this QP value, it's gradually going down. This gray line here is just the average of the value of all features. So we can think about this in 2 ways. We can just calculate the mean value of all the features compared to other sources, or we run PCA. So the gray value will sometimes have lower values than the PCA results. So that tells us machine learning, like PCA, can give us slightly better selection than just directly calculate the average of the features. Now we are doing something like try to extend our results, but those are like optional. Those are not we want to put in the pipeline. The pipeline stop here. It's just that we use this value, this QP value, can select out candidates. But later we're just thinking, can we extend this? So for the creator field I showed you before, we can select out sources with high PCM1 value. Then we can want to combine the results of several exposures and see what remain. So some variable stars show up. Yeah, that's nice. That's what's studied in that paper. But you also find something here. That's the asteroid. Because asteroid is pretty bright. It's about 20 magnitude in those exposures, so it can also captured by the algorithm. Another example is we can extend this idea even further. If we divide the sky into grid, then we can count in each pixel, like super pixel on the sky, how many sources are selected in exposure, and then we combine several exposures. if one pixel, a superpixel, has a large value, that means something repeatedly showing up there in those different images, and it's very likely a real thing. And then we just want to try if we consider this with different weights, like T effective or the PSA performance, how the results will look like. It looks like if we use the PSA1 rank or the PSA1 quantile, we can get pretty. Okay, let me just make a summary. So for the ML pipeline, we start from raw data, and then we make different images, and then run real bogus calculation on single exposures. And for the real bogus calculation, we are using PSA to select other candidates in each exposure. And then for the future work, we want to test different algorithms, different templates, and we are start to build this cloud-based large-scale processing platform. We also want to use source suggestion to definitely I want to thank the DM team and the CTL team for their help. They helped me. And going back to the topic of the session, just for the time domain, I think one thing would be very interesting is the image direction between co-ed image and the co-ed images, or the co-edition of different images. Yes, they were talking to me. This is another way to do this, but that would be very helpful to look for the fin transients. The other thing maybe we can think about is cutouts for transients. It's helpful for understanding the environment of transient and schematics and training for image-based classification. I know a lot of researchers have been doing this, but yeah, believe later in the future we will have better algorithms and better results. Okay, that's all. Thank you.
I can ask. Oh, yeah, there's a question.
Yeah, thanks for the talk. That last item, cutout for transients. So in the presence of real life, which is incompletely detected satellite streaks, you want to know something about context on large angular scales. Yeah. And the question, therefore, is how big of a cutout is possible and needed?
Yeah. So maybe I can answer this in this way. So if you just connect to the pipeline I'm talking about, at the beginning, we are just thinking about we are building something above the broker. So after we get data from a telescope, we process the data with this, so we can reduce the burden of the broker. So maybe the broker also have information of our satellite, not only the stars, we already know, maybe also satellite. Then maybe this question can be solved by brokers.
Anyone else have any questions?
So you talked about the difference between the getting fluxes from the difference images and the total flux,
Yes.
and the fact that the difference images had tied a scatter to it.
Yes.
So do you have thoughts on, with things like variable stars, you do want to know what the underlying flux is. Do you have thoughts on the best way to represent that or calculate that?
Yeah, let me go back to the variable stars. I think for variable stars, usually at first we saw the environment can be a big factor. If the blending is strong, maybe the performance will be very different. But from the light curves I'm showing you here, for a very diffuse galaxy and the bulge data, actually the light curve doesn't look so different. But if we measure photometry from the direct image, you can get, the photometry right. But for the difference image, if we have some ways to determine the 0 point, yeah, this is also like alternative ways to do this. But we just want to make sure we use flags to remove artifacts first.
Right, but But do you think there's ways of maybe using the co-added data or the time series data to get a better sense of what a 0 point might actually look like for the difference images?
I think one thing we could do is we can get light curves from the direct image, and then we can compare this light curve with the previous results, especially this one, we have a lot of OGO results. So they can give at least the first order answer. And then we can improve that based on. Yeah.
I just said you can't get at the DC signal from the AC signal. It's just it's not, the information is not there in the data.
Yeah, I was just wondering if you'd learned something from the time series in the AC signal that would give you a better. Sorry, if you could learn something from the time series, would give you a better estimate of what the underlying DC component was.
Only if you know the amplitude of the variable, and you in general you don't. I had this argument with Zinski years ago, and I was wrong.
Okay. Let's thank Shenming one more time. And now we can move on to our next speaker, Adam Bolton.
Great. So I have 20 minutes. I'm hoping not to use all of them just with talking. For those of you who know me or who don't know me, you might have heard on Monday, I just recently, as of last week, have started here at SLAC as part of the Rubin Observatory team, leading the US data facility effort here. So for the benefit of this session, maybe I'm still new enough that I haven't learned what not to say. So please do, in any discussion that follows, please do bring things up. My goal here is really to just kick off or move forward a little bit more of the conversation around the broader questions of data mobility, particularly large-scale data mobility for LSST data, and the role of the Rubin US data facility in helping that to happen. And there, of course, there's much more to say about all of this that won't fit in today's session, but that we can make sure that everybody who wants to be plugged in is plugged into that discussion going forward. So just a quick overview of the US data facility for those who haven't been introduced to it. This is the central hub for Rubin science data. It's receives the data from the summit in real time, does the prompt processing and alert distribution, archives the data for the long term, handles data release processing and collaboration data facilities, and also in combination with IDAX and the Rubin Science platform, supports the release of data to the scientific community. It's hosted here on the SLAC site in the SLAC Shared Scientific Data Facility, or S3DF. That's within a larger physical building, the Stanford Research Computing Facility. If you're driving by on 280 and you look through the eucalyptus trees and just the right point, you can catch a glimpse of it. And it has the benefit of leveraging both the SLAC and Stanford research computing scale and IT professionals for cybersecurity and user management and networking and such. And then the USDF team as part of the broader Rubin data management department within operations, based primarily at Slack, but with team members at other locations as well. And again, with very close coordination with other sites and other teams. Just to put in a little bit of context here. So schematic data flow, the universe delivers plane waves. The telescope converts them into converging spherical waves. The camera converts them into raw data, and then the data facility converts them into processed scientific data, which goes out through a few different channels here. You'll hear from Christina about the role of the science platform in supporting the scientific community and the science collaborations. What I really want to focus on here in the next few slides is particularly this question of how other analysis facilities are or will be part of the picture in supporting Rubin science. So the overarching goal, of course, is to maximize the science return from LSST. There are, as I'm sure most people are aware, there are a lot of different use cases for image cutouts and processing or reprocessing of LSST data, possibly at very ambitious scales. That includes AI and machine learning. It includes computationally intensive analysis, rerunning of pipelines, joint pixel level processing. One could add other things to this list here. This is just a selection. Some of this work will be supported by Rubin systems, by the Rubin Science Platform, by power user accounts that we're expecting to support at the USDF, and then through in-kind resources provided through the network of independent data access centers and scientific processing centers. But we also want to empower other analysis facilities here. There are community aspirations for science with Rubin data that will outstrip any Rubin specific or Rubin allocated computing resources. And this requires, of course, data mobility. And we think about this in terms of a bulk transfer capability. This is part of the Rubin concept of operations. And it's something that we're now at the point of wanting to further define and plan and coordinate. So what does that coordination look like, just at least in outline form? There are, of course, many different possible bulk transfer clients, many possible analysis facilities that people might want to use to work with Rubin data. That, of course, includes, as we already mentioned, IDACs and scientific processing centers, either through the in-kind program or possibly through other channels as well. The Dark Energy Science Collaboration will be doing most of their analysis at NERSC. There are NSF-funded HPC centers such as TAC, and their resource allocation initiatives. There's Access. There's the National AI Research Resource Pilot, which is another thing that eventually will lead to another context for Rubin data and Rubin science. There's the Link project. There are potentially even campus level research computing centers that might want big pieces of the data. DOE, looking towards the future, is conceptualizing something known as the high performance data facility. So all of this is part of the larger landscape that we're considering. Other particular factors to consider, of course, the data volumes here are potentially large. If you're looking to get catalogs, that's one thing, but if you're looking to get images, that's of course another. Then you're in the scale of petabytes. We do want to align the efforts here with data previews and data releases, and want to flag DP1 in particular. This is the data preview of ComCam data that will come out in early or mid 2025. It really is a good opportunity to roll this out and work out the kinks and make sure everything is functioning in advance of DP1 DP2 and DR1 after that. Of course, this all needs to balance competing priorities, limited staff time, network bandwidth limits. So it will require some further planning. The baseline plan for how to support this is to use the Rusio tool for bulk data distribution. This is a multi-site data management tool that comes from the high energy physics community. It's already being deployed for the multi-site processing amongst the three partner sites in Rubin data release production. This allows the host site or the server site to orchestrate transfers throughout the network. So it's possible to share things in a sort of I guess, like a content distribution like model. Enables defining rules for which data products to transfer to where. It does require local expertise at the various mirror sites to be able to set up the required infrastructure and make sure it's running. A few more open questions and action items. Of course, there's the need to implement data rights at the mirror sites. I believe Rubin can offer at least one solution for that, but there may be others to consider as well. There are questions of how much to integrate with local instances of the Rubin data butler, how to coordinate with the in-kind program, and other bulk data consumers and compute resources provided through that channel. There are also, I think, and this is maybe even getting into another session or another talk, as to whether particular AI workflows or really large-scale analysis workflows might even call for different data formats or repackaging or different interfaces to support cutouts at scale, for instance. We just decided, I think, lunch, and I think it's the right decision, to coordinate this going forward in the IDAC coordination group channel in Slack. I believe this has been private, but now is public. I'm looking for Knut or Sierra to confirm that. Okay, but will be soon. That's, again, I know a lot of the IDAC coordination has been in the a lot of independent data access centers talking about how we together implement this this data mobility and bulk transfer as we go into operations and start seeing the first scientific data previews and data releases. And then my own, I guess I'll plant a flag here and commit myself to drafting a bulk download policies and procedures tech note probably in the next month or two. I'll say two. I'll say end of August, and then I'll see if something gets in the way of that. But that's what I'll say here. So that's all I had, and very much happy to hear any discussions or question around this. Again, there's lots of detail that we could go into and that we should go into in subsequent follow-up. But right now, I just want to make sure that people have an opportunity to hook into this conversation. If you're representing a community or an institution or a facility that has a stake in the success of this bulk data federation model.
So let's thank Adam and move into questions. Questions or concerns or ideas?
If we have any.
Oh, there are two.
Hi, Adam. Maybe an ill-defined question, but I was thinking of in-kind contributions. So for other large groups, perhaps connected with Rubin in various ways, is there a flow back into this, say, high-level data products or things of that sort?
Yeah, that's a great question. I think the short answer is yes. In detail, I don't know how well mapped out that is. I don't know if anyone else here is, but that's it potentially, I think, is something to bundle into this conversation. I know there's certainly a number of data sets that are already envisioned to be provided through the in-kind program. Those are primarily hosted through those other sites, but yeah, in principle, bringing things back into the system is something we could do as well. I guess this used to go under the heading of L3 data products, and then I feel like I stopped hearing that terminology at some point. So I don't know where that stands in official terms right now. Does anybody else know?
Yeah, we changed the name. Leanne will know. Oh, Gregory will know. They are called user-generated data products, according to Gregory Dubois-Felsman.
Hello, can you hear me?
Yes.
Yeah, sorry, I had a bit of a challenge there on muting. Yes, Robert is correct. They were originally called Level 3. They are now called user-generated data products. We have not forgotten about them. And we are, I'd say we're thinking about how we flow back feedback from the community up into how we support user-generated products and how we flow feedback from the community into them.
Go ahead.
I think that was
So
the question. I'm not sure.
So changing the question a bit, when you're thinking about images and bulk downloads of images, is in terms of Rusio, you thinking of somewhat a little bit like the brokers, where you have a community that has different subsets of the data, and when someone is actually wanting to do some bulk download, Rusio handles this for you in terms of where the data reside in some peer-to-peer way, or is this a different model that you're thinking of?
Yeah, I think it can all be orchestrated through Rusio. I think it doesn't necessarily need to be automated. I think it is possible to specify these data are going to go here from there. In terms of distribution out to the IDAC sites, the in-kind coordination group has already got a pretty good framework for mapping out the demand, as it were, at that level. So I think filling that out, first getting a sense for how many different, if it's 5 places, that's different than 50 places, and it may require a different solution. So I think at least making sure we have all of the major potential use cases at the table right now is then can inform the more detailed answers to how that distribution sets up, and whether it can all just fan out, or whether it needs to be like more of a daisy chain type of thing that's managed in some way.
So from a kind of a university perspective, thinking that you might like to download a subset of areas on the sky you're particularly interested, we'd be very happy to be guinea pigs in that process.
Great.
There's a question on Slack. Any comments about data transfer to the Chilean DSE? In the current plan, there are some virtual tables queried on demand.
Yeah, so I don't know if that may be a question for Will in terms of the implementation of the Chilean DAC, and then.
Yeah, so you asked questions online, but the Chilean DAC at the moment, the exact contents of that have not been defined, and it's a conversation that we're having with the Chileans, like which data sets are going to be there exactly, because there's a limited amount of space. One thing that I've discussed is, well, like one of the original ideas was, oh, you put all the catalogs in Chile, and I'm not sure that's a great idea because it uses up all the space. So I've suggested that, in fact, what you want to do is probably just query the QServ back here, like everybody else, because that's going to be beefy and answer queries quickly, and then consider which data it makes sense to put in Chile. The transfers, as far as I understand, we'll do them with Rusio, the same as we do for anything else. We'll find what data set goes there, we'll bring it there, because it's still it's distinct from the fact that we have all the raw data in Chile, and we do all of this embargo, and we do all the other things that we're doing. This is a data center. It'll have it'll be in the same room on the base, but it'll be a different set of machines with a different disk, and so it'll be set up like that. I hope that's a good enough answer, and discussions are in progress.
Yeah, and this is on Slack, so you can also chat with them.
Yeah, I think we absolutely would want the right people from the Chilean community to be in the general IDAC coordination conversation. Again, because we don't want everyone except the US and Chile to get far out in front of where the US and Chilean communities are with this.
I see a question over there.
Interested in a particular use case of gravitational wave detection that is issued very quickly, and our job with LSST is to follow it up as rapidly as possible. But in the process of, so those folks actually have to do a pretty big computer calculation in order to get the area on the sky likelihood plot. And all of this makes use of all of the data around that part of the sky. It seems logical to have all of that done at Slack. Is that possible?
So I'm imagining there's someone here who knows more about the TOO plan than me. But I would, okay.
He's in. Igor would have been a better person to answer. We're expecting to take TOOs not just from LIGO, because if we do it only from LIGO, we'll never do it from anybody else. So I think originally it was Super K and IceCube were the other two candidates. Not that we'll ever get one, but just to be clear. And I believe it's still true that we will ask them to give us the priority, is to give us the logic for choosing priority on the sky, and we will then inject that into our scheduler. That doesn't seem like a big compute load to me. I mean, we're not going to redo the gravitational wave cross correlations to find the area on sky. And the field of view, as you know, Tony, is 10 degrees. So we're not going to micro choose, we're going to look at this cluster of galaxies or anything like that. So as far as I know, we're going to take enough information to feed into our scheduler, and we're going to try it out this LIGO run, because they've extended OCX5 or something. So we will have it in place, but I don't believe it's, what's his name? Adam. It's not Adam's problem.
Yeah, I guess from the computing side, it looks just like alert production and prompt processing in the same routine sense.
Well, the area on the sky is pretty large for many of these, particularly the neutrino.
I guess it would only, if the cadence got faster than the regular survey cadence, then maybe that starts to stress the system, but I don't think it will.
I see there's a question over there.
So I've got two quick questions. The first one was around the, many of the IDACs will just take a light table. The definition of what's in the light table isn't defined yet. So that's kind of a question for kind of what's the timeline for defining that. And my second question is around, part of what we're talking about here is image cutouts for often for machine learning. And it, I can't remember the IDAC structures enough for kind of whether there are IDACs that are better set up to have a set of like standard image cutouts with GPU backup that might be great for kind of people to access and kind of be using that resource, or whether everybody should just come to Slack to do that kind of work, which you probably don't want.
Yeah, so I think the first one is, and maybe part of the second one, are a question for Knut, just behind you there, if the microphone could make its way back around. Yeah, I mean, people who are looking to do massively computationally intensive things with image cutouts, that almost certainly would, I can imagine that exceeding the capacity at Slack. So yeah, I think that's exactly the kind of thing that we'd like to open up to be able to do in other places where other resources can be found.
Yeah, on the object light catalog, I think it's on us as the IDAC coordination group, the set of IDACs and the use cases that they want to enable to define the object light catalog. So since this isn't going to appear out of thin air, I'm going to probably just make a proposal and let people take shots at it.
I'm going to ask you a question, Adam. In this entire kind of coordination, do the science collaborations or the working groups within specific science collaborations, because I'm assuming within working groups, there might be a lot of overlap in what cutouts might be wanted. So if each working group or collaboration as a whole comes up with a list, okay, we would like to maintain this set of objects and this size cutouts for every one of them, so that the thing is not repeated by multiple users. Is that helpful from working groups within science collaborations for this IDAC coordination?
I think the answer is absolutely yes. And I think some of that has also been already, there was a workshop that was, I think it was a link workshop that flowed some of this down from science use cases into, so we may already be partway down this road, but yeah, in general, I would expect the science collaborations to be one of the primary places where some of these more ambitious computing aspirations would come from.
Any last remaining questions for Adam? If not, let's thank him again. And now we'll have Christina Williams for the tutorial on image cutouts and future plans for it.
Hi, my name is Christina Williams. I am an assistant astronomer at Noir Lab, and I'm also a member of the Rubin community science team. And as part of my work on that team, I developed a tutorial notebook to demonstrate the current existing functionality of the Rubin image cutout service. So the cutout service is a really nice attribute to have because, as we all know, the LSST images are very large. So both the individual exposures taken on sky as part of the sort of the nightly survey data, but also the deep coads that come out of the full stack of imaging taken over the lifetime of the survey. And so these images being very large, it's convenient to have a cutout tool that allows us to take smaller chunks of regions of interest and transfer those instead of the very large images. So this is a brief outline of what I'm going to talk about. So I'm going to start with a brief introduction to the International Virtual Observatory Alliance, which defines some of the functionality of the virtual observatory infrastructure. And Rubin has built its architecture around being compliant with the virtual observatory, and that's where we get this cutout tool functionality from. So I'm going to go over a brief introduction of that. I'm going to demonstrate a little bit about the technical explanation that will be in the notebook that I show later in the tutorial, in the talk. So I'm going to demonstrate a small part of this tutorial notebook that we developed with the community science team that uses a science example to demonstrate the functionality. And then at the end, we'll have some time for questions and discussion of future functionality. And so I also hope that you can post your questions in the Slack because we may not know some of the answers yet. And so it would be useful to keep record of those so we can get you answers later. So here I'm just showing some real DP0.2 image cutouts that were made with the image cutout service from the simulated data that's in the Rubin Science platform. All right, so the International Virtual Observatory Alliance is an organization that decides the technical standards for building the virtual observatory. And the virtual observatory is this vision that astronomical data sets should be seamless as a whole, and they provide definitions for those things. And where possible, Rubin Observatory has adopted a virtual observatory first approach to our architecture. And so IVOA standards are adopted. And this is what gives us access to using the cutout tool that is part of the virtual observatory. Some other things you might be familiar with that are part of the virtual observatory definition is like the table access protocol or the TAP service. But this is also something that is IVOA compliant that we use. So the IVOA has defined such that there is a tool that performs data processing and operations on the remote server side. So you don't have to do these operations locally and transfer the whole image over. So this is for short called SODA, the SODA service. So it's a web service that allows you to do these operations on the server side. Some of these things include filtering, transformations, pixel operations. It also includes image cutouts done remotely, which is what the topic of this session is. So I have some links here for more details. And in particular, the way that this is enabled is it makes use of this data link service. And so the location of the remote image that you want to take a cutout of is accessed via this data link. And it points to the data set and the metadata for that data set and allows you to tell the server where that data is to do the operation remotely. Okay, so this is just a brief, very simplified schematic of the procedure that is followed. So you start with an array and DEC of interest for your astronomical object. You perform a TAP query to a table called the IVOA OBSCORE table. And this is holding the metadata and the location of the LSST imaging on the remote server side. So you do this query, you receive a unique URL that identifies the remote location of that data. And so this is what we call the data link, and that's going to enable your RSP platform to communicate with and point to the data set that you want to cut out from. So then you provide this data link that you've retrieved from your tap query to the Rubin cutout service. So this is, the SOTA service is contained inside a PyVO Python package, which you can import as when you're on the Rubin Science platform. And then once you have this SOTA service class, you can then define the cutout region that you want. So this little cutout that you make an image from, and then you can save, you tell the remote server, this is the cutout that I want to make from this image that's pointed to by this URL. And then you can save the file locally on your machine rather than transfer the whole patch and tracked image to your hard drive. Okay, so now I'm going to swap over to demonstrate how this works in practice with a tutorial notebook on the Rubin Science platform. So earlier I posted links to both the GitHub page that shows the actual notebook from our the community science team's tutorial notebooks repo on GitHub. So it's called DP0.213 tutorial notebook 13A. If you don't want to look at the GitHub code or the notebook on the RSP, you can look at a rendered version. It's the top link there. There's an HTML version that shows you all the output, so you can look at that if you'd like. Also, if you want to follow along, you can log into your Rubin Science platform account, and your tutorial notebooks directory should already have a copy of this. All right, so I'm going to stop sharing here and change to share my screen in the Rubin Science platform. Okay. So I sort of went through some of this introductory material already just now. So we're going to import some packages. Importantly, we're going to import these packages from the PyVO package, which contain the access to the SOTA service, which performs the cutout on the remote server. There's some other packages here, the Rubin tap service utilities and some AstroPy and plotting things. So there's a few convenience things we're going to do up front. First is just to make our images and plots look nice. We're going to set some settings for plotting. Right now, the way that the image cutout service works is you first download the cutout in FITS file format on your Rubin Science platform drive. So we're just going to set this definition here to say that we want those to be saved in this temp directory. Okay, so in the beginning of this notebook, there's also some convenience functions, which I won't go through all of them. This one is just to make it easy to plot images from the LSST image format. And then this make image cutout function is one that just wraps all of those steps from the workflow that I showed into a convenient function. So I'm first going to go through all the steps that this function does, and then I'll show you that you can just run it all from this function later. And this is, something that works easily now with the current functionality, but keep in mind when we go to the questions of future functionality later, this may become obsolete. But anyway, there's a way to just, feel free to copy this function in your own testing on the RSP. All right, so we're going to compile that. Here's two things I'm not going to go through. I'm just going to go through part of this notebook just to demonstrate how it works in the interest of time. But if you're interested in seeing more science demonstrations, there are some at the end that you can go through. Okay, so the first step is to initiate the tap service. So I'm going to do that here. And the tap service is going to allow us to figure out, we're going to query the tap service to figure out which image is the one that contains the RA index of interest that we want. So we've already picked out an RA index here of a location in the simulated DP0.2 data set, which has a nice galaxy cluster. So it's a nice target to make a cutout of. So the first thing we're going to do is define the RA index, and then we're going to query this ivoa.obscore table, which contains the remote location of the various images. And it tells you also which patch and tract from the deep coad imaging would contain this RA index. So for this example, we're just going to do deep coads, but you can also use the cutout service for CalX files or other types of images that are in the RSP. All right, so I'm going to run this query. It's going to return to us the patch and tract that contain this RA index location in the deep coad data set. So, and we're going to put that together. We're just going to sort of arbitrarily say we're going to make a cutout of the I-band imaging. So we're going to make a data ID that defines the patch tract and the filter that we want to make a cutout of. So that's what's stored in this data ID. And now we're going to query the ivoa.obscore table again for this thing called an access URL. And the access URL stores the location on the remote server of this one patch and tract and filter image of the deep coat imaging that we want to make a cutout of. So I'm going to make that query to retrieve this access URL. And here you can see it here. So here's the table that's returned from this query to the ivoa.obscore table. And this access URL is the unique, universal, unique identifier of the location of this image. So this is what we're going to need in order to have the remote server do a cutout for us. Okay, so we're going to store this URL as data link URL. And we're going to define it as a data link here. And then we're going to feed this data link to the SOTA service. So this box here is what calls the Rubin cutout image. So we define, so we're going to send this data link to the SOTA service, and we're going to request that the SOTA service perform a cutout on it. So this whole, this sort of instance of SOTA query is, we're going to store this in SQ. Now this thing is basically storing the location of the remote imaging that we want to make a cutout of, and it's also telling the remote server that we want to make a cutout of this image. So now it's time to define the cutout that you want to make out of this image. So right now there's two functionalities for creating, defining the cutouts. The first is by picking a circle of a certain radius, and it will return a cutout that is the square sort of subtended by this circle. So just, so this example is just going to say, let's make a circle of a radius 0.05 degrees. So this means that the square that's returned is going to be 0.1 square degrees on the side. So we define that, and then we say we can use this PyVO function circle to tell this SOTA query instance that points to our remote imaging that we're going to want to make a cutout of this size. So we're going to do this. By default, right now, the functionality is that once you perform this circular cutout on the remote server end, it's going to store you're going to download this FITS file and have to store it on your hard drive. So we do that with this execute stream function. Okay, and then earlier we defined this little cutout function to plot the resulting FITS file. So I'm going to let this chug for a second, and then you're going to see the cutout that we downloaded. So here's the galaxy cluster that we made a small cutout of from the remote deep coat imaging. So there's one other way there's one other method you can use to define a cutout. So that one is by default a square that is, that's subtended a circle, but you can also define a polygon. So when you do a polygon, you have a little bit more flexibility because you can make a rectangle instead of a perfect square. So there you would then define the four corners of the polygon. So here we're just going to do a more rectangular shape by saying that we want the corners to be 0.1 square degrees on one side and 0.3 square degrees, or it's not square, sorry, 0.1 and 0.303 degrees on a side. You don't by default have to do, it's sort of assumed that the fourth corner will be the beginning again. So we're going to do that one. And in this case, we get a rectangular cutout that will appear in a second. It finishes computing. All right, so this is our rectangular cutout. So an important thing to note here is that when you do the polygon, if you want to have, you need to correct for the cosine declination term in the RA direction. So this is just to point out that that's the case. So we've wrapped this whole thing into just a convenience function called make image cutout. So that's easy to copy over if you want to use this now in your own RSP development. So I'm just demonstrating here that for that you can feed it a different cutout size here, and it will, this little convenience function will do all those actions for you. So here's the last one. Okay, so the rest of this notebook has more science examples. So if you're interested to either see a science example demonstrating a use case with a transient phenomena, there's one at the end of this notebook, and also for just visually inspecting deep coads, there's another one later in the tutorial. So I'm going to stop sharing this now, and I think we can move back to future functionality and questions. So let me share my screen again. Okay. So Gregory has helped me put together the future direction slides. And so some of the future directions that we think will happen is that right now you can only do this by querying the obstab and making sort of cutouts out of patch scale images. But in the future, we are hoping to have a sort of more seamless process where you can get cutouts from anywhere without defining the patch and tract first. So that would also include locations near the boundaries of the patches and tracts, which right now are separated in deep coads. But hopefully the plan is to have, you can just feed an RA and DEC to the cutout service, and it will not deal with the patches and tracts at all, and just send you back a cutout without you defining the patch and tract in advance. Gregory, please feel free to, if I skip something important, please feel free to chime in. Okay, sure. Did I catch everything from that slide, or okay, all right, so I'll go to the next slide. So we're also,
yeah, I mean, you know, you're seeing a work in progress. There's a lot of kind of boilerplate rigmarole in what Christina showed. Those are the steps that are happening underneath, and finding the image and locating in the service and calling the service and so on. But we can wrap that up in more convenient Python layers. And so ultimately, if you've already gotten a data ID, which is where Christina started from, basically in doing this, there's no reason why that whole thing couldn't be wrapped up more. And so that's just, you're just seeing the sort of limited resources we've had to put the kind of final layer of polish on top of things. So we're going to be working on that. And that will also work nicely with what was on the previous slide about making cutouts from coads without having to first find the coadded images, because that's obviously, you're doing the same thing twice. You're providing the position you want to the image service to look up the image, and then you're providing position again to the cutout service to give it the template, and that's clearly not necessary. You might be saying, well, couldn't I just load the image into my notebook and do the cutout in my notebook? And ultimately, that's probably not what we want, because you're bringing all of that data from the USDF into the cloud, into your notebook, just to make a cutout from it that is then what you want in your notebook. So we want to have the cutout service at the USDF so that it's next to the data, and that you don't have to move as much data into the cloud, into your notebook computation. So making this easier is ultimately a much better solution than what right now looks easier, which is to just use the LSST stack to do the cutout locally in your notebook.
there's some problem with the sharing screen. Yeah, and I can't actually access it. It's not letting me. Oh. Okay. Great. All right. So Did you?
So with regard to bulk cutouts, there was quite a bit of a discussion of this earlier. So I thought I'd describe what our strategy for this is. We have a requirement to support bulk cutouts. It's relatively limited. I'm sure if you, by the time you've read the numbers in that bullet, you're like, what? But that's what was in the requirements. That's been there for a long time. And we will certainly provide a service meeting the specification, and we can provide additional hardware backing it up to scale it up if, depending on what the load is. So that addresses the use case of many cutouts of the same location in the sky across many epochs. So that's the kind of the film strip, if you like, associated with a varying source, for instance. So that's the science use case for that. But more generally, obviously, if people are asking for bulk cutouts, they could also mean across many targets. And we recognize that the utility of a multi-target service, and we'll explore seeing if we can have it have that capability as well. So we're looking into suitable output data formats and structures for bulk cutouts. It's kind of inconvenient to ultimately, for like full 10-year depth, to provide 800 separate extensions in a FITS file. It's not a great interface for people trying to browse the data. A cube's not a great solution either, because it doesn't work very well if it's a moving object and it's the center of each one is at a different position. There's no way to represent such a WCS cleanly in FITS. So we're looking into what the right set of data structures is. It's related to work from some other projects that have similar requirements, one of which I work on as well. So we're trying to figure out what the best available solution for that is. Yeah, that's work in progress as well. It's a priority 2 requirement, so that's operations era. So that won't be available until probably well into the first year, or at around maybe as late as DR1, the formal definition of our requirements.
So that's basically it. But we're happy to take questions and collect them if we don't have the answers, so we can find out the answers for you. Gregor may already know the answers. So yeah, we also have some links to some RSP tech notes that may have more detailed information for you.
So let's thank both the speakers. Now we'll take questions.
Yes, thanks. That was a great talk. I guess on the previous slide, that second bullet for future functionality would sort of serve the AI-driven training set use case, where I mean, you might want like 1 million cutouts of small size, single objects, but lots of them, right? And you want that in a reasonable time. And so if it takes 10 seconds for the cutout from one object, that would be half a year, right? Yeah.
That's why I said you would probably react to the numbers. Our scope resources are what they are right now, right? And this will evolve as we start operations and as the value of the data becomes clearer. If we have a beautifully working observatory and we have an overload of people trying to do good science with it, that leads to conversations with the funding agencies that can let us scale things up that we don't have the resources to scale up right up front. So we can't, I can't make promises about that, but as well as I do, the way things are likely to play themselves out, it's a much better story once you've shown the observatory is working. So.
Yep.
Hi there. Thanks very much for a super interesting talk. So we're already on the science platform querying for tens of thousands of small cutouts. And I'm wondering whether you have some advice for us in terms of picking up what you're developing here and trying to make what we're doing as efficient as possible. And I wonder if there's something we could do in terms of being a bit cleverer about identifying the patch and tract so that we can, make all the cutouts we need to from a given patch before moving on to the next one. Is there some efficiency gain we can make there rather than just doing a simple loop over?
Yeah, I mean, definitely. I mean, that's one of the reasons why, if you go back one slide, like why having a multi-target cutout service is valuable, because it can do that kind of optimization. It can identify how to cluster the cutout requests so that they're satisfied by data that's co-located. If you're, for instance, if you're doing cutouts on, members of a cluster or something like that, where they're all in the same part of the sky. So, but if you're asking what could you do as a user now, kind of one-on-one, I could give you advice, but that doesn't scale very well right now. To our also having enough attention to finish the services that we need to finish. So I think we can use existing communication tools like Community to have discussions about that and each learn something from it. I'd like to explore what you could do if you are driving them yourself, as opposed to waiting for us to finish the optimized service.
Yeah, understood. I mean, we're happy to share the notebooks as we make them as well.
Yeah, that'd be cool.
I was just wondering whether, after we've done the sensible thing of focusing on one patch at a time, is there any other speed up that the multi-target service will be able to do beyond that? I mean, do you see, other tricks that you can play that we can't?
I mean, yeah, to some extent, particularly. I mean, I don't know how your notebook is doing the cutouts. So I can't really, without seeing it, I can't tell you.
It's just a for loop.
Yeah, but a for loop over what? Over calling the cutout service?
Well,
or out of doing them yourself with AFW?
Well, imagine that we pick up the cutout service and we take Christina's notebook and we just call it, put the make.
Yeah, I mean, of course you can. I mean, there are things that could be done better than that, but I think you won't be able to do any better than that by iterating over calls to the cutout service right now. There's most of the inefficiency comes from that overhead of making those individual calls. Because right now it's not really, it's not attempting to do any caching on the back end, so that you call it again, and so that's why I'd like to. I mean, if you need something soon, we can talk about what you could do to do this in a slightly different way. But in the long run, the right answer is the multi cutout service. Okay. I guess technically, the multiple cutouts for many epochs is a construction requirement. So we can't ask for in-kind assistance with that, but we could ask for in-kind assistance with this, because this is formally not a construction requirement. So if you're interested in helping, you could have a conversation.
There's a question over there.
Yeah, pardon for an ignorant technical questions. I don't know anything about how images are stored or represented in the data storage. Is there, though, some form of query or some request to some patch which would be particularly well suited to the architecture that would enable more rapid bulk follow-ups, as opposed to saying, I want a precise patch of a such and such a size with a thing at the middle where you might ask for a segment that could be very easily produced?
Not really, obviously. If you're just talking about, like, when you said rapid follow-up, you mean if you were trying to get cutouts associated with an alert or something?
Question of a large bulk download.
Yeah.
And, if they're pre-cooked, little patches, that would be one thing. And it
no, we don't have anything like that.
No, but I was asking, is there an architecture where it makes sense to ask for one form of cutout as opposed to another that would speed?
Not right now. Okay. No. That's something. I think that kind of a design is something I'd like to see what the actual load looks like, and then think about an optimal architecture after the shape of the load is clearer, because it depends on whether we're mostly getting things scattered all over the sky, or we tend to get like, you know, everyone's trying to look at a few nearby galaxies, or, you know, or people only care about supernovae, and so caching them would be good because everyone's looking at the same ones, or like, you get different answers depending on what the actual usage pattern is. So don't really want to pre-commit to that, but we will, in general, hopefully will nod here, be looking at the load, not just on cutout services, but at queries and everything else throughout operations, and trying to build a better system to meet them as we go. You know, what you get on day one is definitely not what you're going to be stuck with for 10 years.
Okay. Unless there are any pressing questions, we are almost at the end of the session. Even if you have questions for any of the speakers, I encourage you to use the Slack channel to ask them. I hope this session was useful and you are leaving here knowing more than what you came in with. And with that, let's thank all the speakers, and I hope you have time to go look at the posters.
Thank you, everyone.